Hello, and welcome to this FMSP Core Prerequisites video. This is the last one of the second set. These videos are designed to help you get ahead with independent study of the A2 core, ready to develop the skills in A2 further maths modules. This is what you should already know. Make sure you're really confident with all of this material before continuing with this video. It's best to do the consolidation work as you go along, rather than watching all the videos and then trying to do the consolidation work. You'll need all of these things, so pause the recording now and go and get everything together. And make sure you set aside enough time to do the questions, as well as watch the video. This is what we'll be covering in this video. We'll start by looking at forming a differential equation. Imagine a population of organisms, perhaps bacteria. The individual organisms reproduce, and this means that the more organisms there are in the population, the faster the population will grow. Suppose the rate of growth is proportional to the size of the population. Can you write an expression for this? Think about what you did about proportionality at GCSE, and pause the video and see if you can write an expression. Okay, let's see what it's supposed to look like. We're talking about the rate of growth of our population, so that will be dp by dt. Rate of growth, the variation of the population p with respect to time. And we're told that this is proportional to the size of the population, so it's proportional to p. And you'll remember from GCSE that that means that dp by dt is equal to k times p for some constant of proportionality, k. Maybe you know what k is, so for a particular population it might be known to be 0.1, and that would give us dp by dt is 0.1p. This is an example of a differential equation, just an equation with a derivative in it. They're used to model situations involving rates of change. This differential equation is called a first-order differential equation because we've just got a first-order derivative and no derivatives of higher order. These are the only sort that you'll meet for Core 4. In this video, we're going to be addressing two skills. First of all, translating a word problem into a differential equation, and secondly, solving first-order differential equations of a particular type which only need one method to solve them. If you go on to look at differential equations in further maths, you'll look at a much wider range of differential equations, but for this video we're just looking at one type. We're going to start with the translation aspect. Sometimes it's simply a matter of reading the question and translating the words into symbols. So, the rate of growth of a population, that's dp by dt, is given by equals 0.05p squared. That's quite straightforward. Here's another one. Now you need to take care here. We've got temperature and time. Time with a small t, temperature with a capital T. Now you know why your teachers have been nagging you all these years about making sure that your small letters and your capital letters are consistent. In maths, a small t and a capital T are as different as a T and a U. So, taking care. The rate at which the temperature is increasing, that's d capital T by d small t, is given by equals 2t plus 0.01 t squared. Here's another one. The population of a region at time t years is decreasing at a rate given by 0.1 pt. But why is that equation incorrect? Well, the population is decreasing, so the derivative should be negative. dp by dt is equal to minus 0.1 pt. Okay, here's another one which is proportional. It's just a matter of picking out the letters. We've got an area A, and the area grows at a rate, so dA by dt, which is proportional to the area, so proportional to A. So dA by dt is equal to K times A. Sometimes we've got a situation where two quantities are connected to each other in a way that we know, and that will lead to a relationship between their rates of change. So consider a square with area A and side S. We know that A equals S squared. What about rates of change? S is increasing with time, would write its rate of change ds by dt. If S is increasing, then so will A be, and its rate of change is dA by dt. We want to relate these two. We start with the equation A equals S squared and differentiate both sides with respect to the same variable t. So the left-hand side is dA by dt. For the right-hand side, we're going to need to use the chain rule. Differentiate with respect to S first, 2s, and then multiply by differentiating S with respect to t. And there's our equation. One more example and then you can have a go. Here we're dealing with a circle, and so our equation is A equals pi r squared. We'll differentiate both sides with respect to t, dA by dt, and then the other side using the chain rule, differentiating with respect to r first, and then dr by dt. Okay, you have a go. Pause the video and try this one. Right, let's see how you got on. We've got deceleration, so we're going to need a minus sign, of a car travelling at velocity v. So deceleration, dv by dt, equals minus, it's proportional to, k, the square of the velocity, v squared. That's d. Okay, try this one. Pause the video and have a go at it. Okay, this one's a bit more complicated. We've got a light source r centimetres from a point, and the light intensity given by this equation I equals 100 over r squared. The light source is moving away at a rate of 0.5. So the light source was r centimetres away, so the rate of change of that distance, dr by dt, we're told is 0.5. And we're asked to find an expression for the rate of change of the light intensity. So we've got I equals 100 over r squared, and we want di by dt. So we're going to differentiate both sides with respect to t. So 100 over r squared is 100r to the minus 2. And if we differentiate that with respect to t, then we'll get minus 200 r to the minus 3 multiplied by dr by dt. So that's minus 200 over r cubed, and dr by dt we're told is a half. So that comes out to be minus 100 over r cubed. But our expressions all involve I and not r. So now I need an expression for r cubed in terms of I. So I had I was equal to 100 over r squared. So r squared is 100 over I, and therefore r is 10 over root I, which means that r cubed is 1000 over root I cubed. Now I can substitute that back in to where I was before. di by dt is minus 100 over 1000 over I cubed. So that's minus root I cubed all over 10. And that's option C. Okay, what about solving them? This is the differential equation that we had at the beginning. dp by dt equals 0.1p. What we mean by solving it is finding an equation connecting p and t which doesn't have a derivative in it. So this process is going to involve integration. We can rewrite this differential equation so that the left-hand side involves only p, and the right-hand side only t. This is called separating the variables. Let's see what it looks like. First of all, we need to separate out the two parts of dp by dt, pretending that it's a fraction, which of course we know it isn't. But often we can treat it like one. So this feels as if I'm multiplying both sides by dt. Then I need to make sure that I've only got p on the left-hand side with the dp, and I haven't got any t's to move to the other side. And now I can put in the integral signs. Integral of 1 over p dp and integral of 0.1 dt. And here you need to take care because you're integrating with respect to different variables on the two sides of the equation. So let's do that. The integral of 1 over p is log p with modulus signs, and the integral of 0.1 is 0.1t, and somewhere here I'm going to need a constant of integration. I'm going to put it on the side which doesn't have the p's, because in the end I want p equals. This type of differential equation is very common, so it's worth being confident about how to move on and tidy it up. If we put both sides to the power p, it is in the end going to make it simpler. So e to the log p equals e to the whole of that the right hand side. Don't try doing e to the 0.1t plus e to the c. It's e to the whole of both sides. And that of course gives us on the right hand side e to the 0.1t times e to the c. Now c is an unknown constant, so e to the c is still a constant, still unknown, so we don't need to call it e to the c, we can call it a. So that gives us e to the log p equals a, e to the 0.1t. Now of course e to the log p is just p, still with our modulus signs there, equals a e to the 0.1t. But p is a population, and you can't have a negative population, so we know that p is bigger than 0. And that means we don't need to bother with the modulus signs, and we get just p equals a e to the 0.1t. This is the general solution of our differential equation. We don't know how the population started, so we don't know what that unknown constant a is. But we might be told some information about the initial situation which enables us to work out a. Suppose we're told that when time is 0, p is 200. Well, in that case, 200 equals a e to the 0. And since e to the 0 is 1, that tells us that a is 200. And we have what's called a particular solution for this particular case when p starts at 200, and that is p equals 200 e to the 0.1t. Let's summarise the method. We start by rearranging the equation so that one side involves one variable and the other side the other. Then we integrate each side to get a general solution, which will include an unknown constant. Then, using the information that's given in the question, we can work out the value of that constant. Sometimes that information is called boundary conditions, sometimes it's called initial conditions, because it tells us what happens at time t equals 0. Here's an example. So, dy by dx equals x cubed over y. separate the variables. So I need the dy on the left hand side and the dx on the right. It feels as if I'm multiplying by dx. That means I need to leave the x cubed there and multiply both sides by y to get y onto the other side. Then I can put in my integral signs. Carrying out the integrations gives me a half y squared on the left hand side and a quarter x to the 4 plus a constant on the right hand side. Too many fractions there, so I think I'll multiply everything by 2 to get y squared equals a half x to the 4 plus, well, a different arbitrary constant, so I'll call it c dashed. No point in calling it 2c when it's arbitrary to start with. Then we're told that when x is 0, y equals 4. So that means that 16 equals 0 plus c dashed, and therefore that c dashed is equal to 16. Our particular solution is therefore y squared equals a half x to the 4 plus 16. Here's another example. It looks very similar, but it's going to turn out to have a very different solution. dy by dx equals y over x squared. So again, leave the dy where it is and appear to multiply by dx. Now I need the x's then on the right hand side, so if I leave that where it is, that's 1 over x squared, and if I divide both sides by y, that gives me 1 over y on the other side. Integrating 1 over y gives me log y. Integrating 1 over x squared gives me minus x to the minus 1 plus constant. Putting both sides to the power e, e to the log y is just y, and that equals e to the minus 1 over x plus c. As before, that's e to the minus 1 over x times e to the c, and we replace e to the c with a different constant a. So I end up with y equals a e to the minus 1 over x. Then we're given some information. Y equals e when x equals 1. So that means that e equals a e to the minus 1. Multiply both sides by e and we get e squared equals a. So our particular solution is y equals e squared e to the minus 1 over x. OK, it's your turn. Pause the video and have a go at this one. Right, let's see how you got on. dy by dx equals x over y cubed. So separate those variables, dy on the left hand side, dx on the right hand side. So leave the x where it is, multiply both sides by y cubed. Put in your integral signs. Now carry out the integration. A quarter y to the 4 equals a half x squared plus constant. Now, looking at the form of the solution, I want y on its own. So let's multiply through by 4. So that's y to the 4 equals 2x squared. And I think at this point I'll change the name of my constant to k. I do need it to be different from the previous line anyway. And then take the fourth root. And there we are. That's option A. OK, here's another one. Pause the video and try this one. Right, let's look at the solution. dy by dx equals sine x. Separate out your variables, so sine x dx. Put in the integral signs. And now do the integration. Integration of 1 dy is y. integral of sine x is minus cos x plus constant. Okay, we're told that x is 0 when y equals 0. So that means that 0 equals, cos of 0 is 1, so that's minus 1. And therefore c is 1. Our particular solution is therefore y equals minus cos x plus 1, or 1 minus cos x. And that's option A again. Okay, that's all the techniques you need, but now you need to do loads of practice, both of translating and solving differential equations. So go and find your Core 4 textbook and complete some of the exercises. Make sure you're really confident with this material so that you're ready to work on the topic with your further maths teachers. I hope you found this video useful. It completes the topic of integration. If you're studying vectors in further maths, I look forward to you joining me for the final set of videos. Goodbye.